What happens when we put two batteries in the same circuit? Stay tuned and we'll take a look in this episode of the Online Physics Teacher. Welcome back to the channel. If this is your first time here, I'm Robin DeMarco, the Online Physics Teacher. And my passion is taking the mystery out of physics and helping to supercharge your science education. For the best information about physics tips and tricks, be sure to subscribe to my channel and hit the bell so that you'll be notified the next time I post a new video, usually every Friday. In last week's video, we looked at what happens when we put series and parallel circuits together, connected to the same battery. This week, we're going to change this a little. We're going to put multiple batteries in the same circuit. Let's head over to the whiteboard and see if we can figure out what's going on. We have already seen the basic form of this circuit. If I cover up this half here, what we have is just a regular circuit that we've already seen before. Now, we do know a few things. We know that the current at any junction will be the sum of the individual currents, and that the voltage drop around the entire circuit is going to be the entire potential difference that we began with. These are the basis for Kirchhoff's rules. Now, Kirchhoff has two rules. The first one is the junction rule, which states that the sum of the currents approaching any junction must be equal to the sum of the currents leaving the junction. The second rule is known as the loop rule, and this says that the sum of all the EMFs, or the voltage sources, and all of the potential drops across the resistors and the other elements must equal zero. So let's take a look at the circuit we've got drawn here and see how this is going to work in an example. We're going to begin by taking a look at the two separate loops here. Now notice we've got the first loop over here, and I'm going to label that as I1. And I am using a common current. So it's coming from the positive going toward the negative. And I'm going to do that with both sides. Now I'm going to color code these because I want you to be able to see these where the pieces are coming from here. So there's I2, again, coming from the positive around to the other side. Okay, let's take a look now at loop 1. The EMF that's in loop 1 is E1. And as we go across, we're going to see that it's I1 going through R1. So we're going to subtract that, I1 minus R1. And now we're going to come into resistance 2. Now there's something that's going to happen here. And I just kind of want to show this. We have two different parts. I1's going this way and I2's going this way. Now some books may show you that you have I3, which is equal to I1 plus I2. Or some may leave it as is. It's I1 plus I2 and work from there. In this example, I'm going to leave it as I1 and I2 here. Okay, so again, we're going to subtract, because remember it's a voltage drop. What I'm going to have here this time is I'm going to have I1 plus I2 times R2. And that whole thing has to equal 0. What I'm going to do here is we'll just expand it out a little bit. And then we're going to put numbers in just to kind of keep this a little bit simpler for us. You'll see why in a minute. So I'll get I1 R1 minus I1 R2 minus I2 R2 equals 0. So what we're going to get here is we're going to have 12.0 minus 4.0 I1 minus 4.0 I1 minus 4.0 I2 equals 0. Combining our like terms, we get that 12.0 minus 8.0 I1 minus 4.0 I2 equals 0. So this is going to be our first equation we're going to look for. All right, loop 2. At this time, again, we're going to have our EMF. Okay, and going around, so we're going to have our EMF. we're going to subtract out, again, I1 plus I2 times R2 minus I2 R3, and that's going to have to equal 0 as well. All right. So what we're going to do is, again, same steps we followed over here. We're going to put them over here. So we get E2 minus I1 R2 minus I2 R2 minus I2 R3 equals 0. Again, putting our numbers in. In this case, E2 is 8 volts, so 8.0 minus R2 is 4, so 4.0 times I1 minus 4.0 I2 minus 2.0 I2, and that equals 0. Combining our like terms gives us 8.0 minus 4.0 I minus 6.0 I2 equals 0. So what I've got here is I have two equations with two unknowns. So what I want to do is we're going to solve these two equations with two unknowns. And we're going to do just a simple mathematic substitution. Okay, so what we want to do now is we need to solve this simultaneously. Easiest thing to do, we're going to multiply the bottom one by a -2. All right. What that'll give us then is, instead of that, we're going to have negative 16.0 plus 8 I1 plus 12.0 I2 still equals 0. So I can cross this line out here, really. And when we go through and add this all together, 12 minus 6 is going to give me a minus 4.0. These are going to cancel out. So my I1 term is going to disappear totally. And then I'm going to have a negative 4 plus 12, which gives me a positive 8 I2 equals 0. And we're going to solve this now for I2. And we get 0.50 amps. And what we're going to do for the last part here is we're going to take this value for I2 and we're going to put it back into one of the equations. So we'll take this one over here and put it back in. We get 12.0 minus 8.0 I1 minus 4.0 times 0.50 equals 0. And let's see, that's going to give us 12.0 minus 8.0 I1 minus 2 equals 0. So I get 10.0 equals a minus 8.0 I2. Oops. I skipped a step there, sorry. Divide both sides by 8.0. And I get that, oops, that should have been I1. That I1 will equal 1.25 amps. It takes a little practice to feel confident solving circuit problems with Kirchhoff's rules, but just keep working on it. You'll get it. If you haven't picked up your free copy of the PDF, 15 Tips to Improve Your Science Grade, I've put a link in the description of this video down below. If you like the video, please let me know by liking it, subscribe, and please share it with someone you think would benefit from it. I'm Robin DeMarco, the online physics teacher. Thanks for watching, and I'll see you on the next episode.